Okay, so here's a thread, and I'll just go with my notes. I won't really write too much. I'll just solve the problem today in class, but the notes are fairly complete. Okay, so when we look at fasteners, we are looking at with few things before we get into stresses. There's a major diameter, minor diameter, pitch diameter, which we should be clear about because it is next going to be used to develop some expressions for the stresses. So the major diameter is the diameter of the outermost part of the uh, fastener. Then we have the minor diameter, the innermost part. So outermost part really would mean, actually it should be this one. That's the outer, major. And the minor diameter would be the one which is the inner one. So the pitch is something which, so the pitch diameter is basically the mean of the two, so major and minor. And the pitch is defined as the distance between two crests or two troughs, okay? Highest points on the screw. Uh, so that's basically what I have defined here. There's something here which is the lead. It is the distance the nut moves parallel to the screw axis when the nut is given one turn. So when you turn this by one turn, the lead gives you how much is the distance traveled. Okay. And one of the things about fasteners or where power screws is that it converts rotary motion to linear motion. So the spinning is then translated to linear motion. And this is good because now mostly you have motors which are turning and spinning in circles. And many times the load which needs to be moved is moving back and forth. So this one will achieve that kind of motion. Okay, so this is just a few more things I talked about. There could be double or triple threads. So this is basically how where the lead comes in. So 2 or 3 times the pitch, then you have double or triple thread. So it moves 2 or 3 pitch. So pitch was the distance between two troughs or crests. If it moves two of those in one turn, then it means that it's a double or triple thread. The two most common threads are the square thread, and these are used for power transmission, and the Acme thread, which is at an angle. Uh, okay. So let's get to the mechanics of power screws. Okay, so as I said, it's a power screw is used to change angular motion to linear motion. So angular rotary motion, motors does rotary motion, and then that would be converted to linear motion with a power screw. Okay, here is a caricature of a screw. So usually there's a screw, there's a nut, which basically is used to attach a screw to the member. Uh, the different things we need to know about this, we've talked about pitch, F is the axial force, the helix angle and the lead angle, you can see over here, this is the lead angle, this is the helix angle. They should add up to 90 degrees, and really this slope, they characterize the slope of the screw. Right, so one of them characterizes the slope with respect to the axis of the screw, and one with respect to a angle 90 degrees. Really don't need both of them, just need one of them. Okay, now our goal here is, as I said, the screw basically helps you to move rods linearly when you spin it. So our goal is to compute the torque needed to raise or lower the load, right? How much force do you need? And that's kind of an important calculation. So this is where we will use some of the tools in statics. On the left side is, so this is just showing one of the threads. So if you have threads, this is one of them, that slope. When you are applying a force to lift the load, so when you're lifting, you're basically sending the screw in that direction, right? So what will happen is the screw will move in this direction, which means that the friction force will oppose. It's going to be direction opposite. There's always a normal force, which is normal to the slope, and then this force here is the force which is an external force, right? you're trying to apply a force PR, which will basically cause this to move up in spite of this force F, which is an external load. Okay, so F is the compressive force, this is the external load. F is the friction coefficient, N is the normal force. These two are the forces which the screw is going to apply. This is the force which the motor will have to supply. And then the mean diameter. So this calculation for figuring out what that PR or PL is, PL is a calculation in statics. You take that free body diagram in the X and Y direction. So that's what I did. So derivation is not very important here. I'm not going to tell you to derive, but you need to know the final result, which is if you take the summation of forces in the X direction, so the X direction happens to be in this way. So they'll resolve. You can see PR is along the X-axis, and then you resolve the normal and friction force. So when you do this in the X direction, you can solve for N. The N is an unknown here. And we'll assume that the friction force is known. So we solve for N, then we do equilibrium in the Y direction. Y is upward direction. When you do the equilibrium, you get another equation, and then this equation will have N, the normal force, which can be now eliminated, right? So you eliminate N and you get an expression for F. So this is what we were after. The force you require to lift a load depends on the external force, the angle of the thread, okay, and then the friction force. Now, tan lambda is L divided by pi dm. That's something which you can see here. So this is pi dm. That's the mean diameter, so it's going to be the circumference. And then L is the distance moved, or the lead, in one rotation. So this angle, lambda, is L divided by pi dm. In fact, tan gamma is L divided by pi dm. So we can actually eliminate sine gamma, cos gamma, because we know what that is. We can actually divide both sides, the numerator denominator, by cos gamma, and basically get the expression which I wrote down here. So this is an expression for the force needed to lift the load. And then the lowering the load works in a similar way. Do force equilibrium, you eventually end up with an expression for the force needed to lower the load. So let me just put that here. It's a good point. Why do we need this? Example would be lifting jack or a car. Okay, so what I've got here is the load, but to convert the load to a torque, which is what we'll be supplying either manually or by a machine, is PR times dm divided by 2. We have assumed the mean diameter, and so the expression from the previous page is just put here, and you get an expression for torque. So these are the two expressions you need. Okay, that's why I box them. You don't have to remember anything else. Okay, so now that we have the expression for the torque needed to raise or lower the load, the lowering is kind of interesting. So imagine that you turn the jack in the car, and you keep applying it, and eventually what happens is some point of time the car is stationary. It's not applying a load to get the jack back. It's because it's self-locking. It's not going to basically move. So there's a condition which prevents the load from going. You lifted the car up, and now the car will not move down. It will the whole system needs to be self-locked. Otherwise, you're going to sit there and apply a force to keep it up. So the condition for self-locking is that TL should be greater than 0, which is this. And basically, that puts a condition on the friction force. So the friction force, if it's greater than the angle of the thread angle, lambda, then it's self-locking. It will not come down, which is a nice thing to have. Okay. So if you know the friction and you know the angle, you can design a screw jack, for example. There's a term called efficiency, which is obtained by putting F, that is the friction, equal to 0 in TR equation. So this is the equation for raising the load. if you put friction equal to 0, so it's the amount of force needed in the absence of friction. There's no friction. How much is the force you would need? That would be the friction actually hurts you, right? When you're trying to apply a load to lift something, friction is slowing you down. So if there's no friction, you have a very efficient screw, which means that you can transmit most power. Everything which you put in will go into the lifting the load, and nothing will go as dissipation through the friction. So that's your case where you have friction of 0 or highly efficient. So that would be a 100%. So that would be T0 divided by TR. Okay, so you can use this to compute the efficiency of the power screw. Okay, so now that we have talked about this, we've only looked at the square thread. If you are looking at an ACME thread, the force is not horizontal. So when we looked at the square thread, the force was like this. If you draw it this way, the force was like so. If the force is at an angle, then you just have to take that alpha, the helix angle, and then you just rotate F, which means that your equations will slightly change. There'll be a secant alpha, which will come there. So that's for the asymmetry thread. Okay, the square thread is more efficient than an asymmetry thread because your force is directly coming normal and it's not coming at an angle, but ACME threads are easier to machine. So it probably means that ACME threads would be cheaper than square threads. So it's a matter of convenience versus efficiency. Okay, a thrust collar is sometimes, you can see a collar here. A thrust collar is sometimes added. It's just to buffer the force. Okay, if you have a thrust collar, then you can draw a free body diagram of the thrust collar. There's a forces, which the net force is F. You will divide it into two forces, and each of these forces are shown with friction. So mu times F divided by 2. These forces form a couple. So we have the torque due to the collar would be 2 times, because the couple, the two forces, mu F divided by 2 is the friction force, and then dm divided by 2. So this is basically the force which is resisting motion as you twist the screw against the collar. Okay, so this is the expression for TC. So there will be an additional torque which comes into play if you have a collar. So because of the friction, of course, if the friction is 0, then you don't have to worry. There's no forces between the two preventing your TC, and TC will be 0, which makes sense. Okay, now we'll come to the most important part, which is you take a power screw and look at what are the stresses on a power screw. Okay, so here is an element. It's blown up. Okay, I've shown the axis. In any element, there are 6 stresses. Now, this is probably the first time where we're doing 3D stresses. Okay, there have been cases where we did 3 stresses for shafts where you looked at 2 planes. That's another way to do it. So here we're going to figure out what are the 6 stresses. Some of them will actually be 0. Okay, so here is, we'll start with sigma y. Okay, sigma y is a compressive force. You can see it will come because of this F. Okay, so there's F on this side, F on that side. It's basically, if you take dr is actually the dr, I think, is the pitch. Let me just check this. Dr minor. Okay, so dr is the minor, which means that this is, oh, there it is, dr. Dr is the minor diameter, so it's between the innermost part of the screws. So why we use the innermost is because the smaller dr is, the bigger the sigma y. So if you take d outer, then the stress will be lower because dr is greater, d is greater than, or dm is greater than dr, and so you'll get less stress. So use the smallest one to get the maximum stress. That will be the part which will have the maximum stress. So compressive stress. So there's that. So we're done with one. Next, we'll look at the bending stress. Okay, so what we need to do for this is kind of interesting. We have a screw, we have these threads. We basically unfold it, which is we basically pull out. So this is one of them is pi dm, right? So it's pi dm is the circumference. So you pull out one, you pull out the second one, you pull out the third one, and you basically line it up. So this unfolding it so that this is pi dm times nt. So number of threads times pi dm will give you the total length. So it's unfolding. Better way to draw it would be if you have. Okay, so if you look at this in the top, well, it's basically wrapped around. You just need to strip it off, and then it will be, or think of taking a thin bar and then wrapping it around. So you take this, put it over here, and then wrap it around like this. Similar thing. So we unwrap it, unfold it. That's what I shown here. Okay. So once we have unfolded it, this is a side view. This is the neutral axis. This is the force F, the same force I drew earlier. And now this beam is subjected to a bending load, just like we've done. So it's a cantilever beam, but we assume that the force is not exactly at the edge, it's exactly in the middle. This is just an approximation. Okay. So this force is acting at a distance of P divided by 4. Again, that's an approximation. The force in the x direction now, remember this will produce a stress in this direction because it's a bending moment. And so that direction is the x direction. So that's my divided by I. M is F times P divided by 4. Y is the distance from neutral axis. Turns out this is the pitch. So it's pitch divided by 2, sorry. And so then that distance of the neutral axis from the top is going to be half of that, so P divided by 4. And then this is going to be BH cube, BH cube. That's basically if you have a beam with height h and b, then the moment of inertia is 112 BH cube, b being this unfolded length. I think it should be m, I think. Check. I think this should be m, not r. Huh, interesting. I think I might have made a mistake. This is using r, not. Yeah, so the reason why you want to use r and not m, again, is the same one as what I told you before. dm being the mean diameter, let's go here. So dm is the mean diameter, this one. And dr is the inner diameter. Okay, so dm is clearly greater than dr, right? Because obviously the mean is greater than the innermost diameter. So if you use the mean diameter here, you'll have smaller stresses because dm and sigma are inversely proportional. So you want to use the minimum possible diameter so that you get the maximum possible stress. So really there's a choice you could make here. We just want to use the minimum one to get the maximum stress, sigma x. That's the reason. You always design based on the worst case. Okay, that's sigma x. There are 3 more stresses we need to look at. So that's just the simplified expression. Sorry. Okay, there's a torsional stress. You can think of the screw as a cylinder with a torque T and a mean diameter. Again, we use dr because it's going to be the minimum diameter will give the maximum stress. This is a formula we've seen before. Torque time rho divided by j. Okay, so just putting the value for rho as dr divided by 2 and then polar moment of inertia, we get expression tau yx phi z. There's one last stress, which is the transverse stress, because because you have these threads and they have a tendency to slide over the cylinder being the shaded part, the pink part slides over the cylinder which is not shaded, you will have a transverse stress. And transverse stress for a cylinder is V divided by A. And so V comes from the torque, and area is basically the area you get when you unfold that. So again, you do the same thing. You have this coil round, you unfold and you make it a thread, which is straight, and then you find how it shears. So that is Zx, and that's the last stress. So there are 4 non-zero stresses, which I will next summarize. Here is a summary. So there are 6 stresses. There are 2 which are 0, tau xy, and sigma z. Now, there is a big assumption here. We assume that all threads carry equal load. So what that means is when you have a screw and just draw the threads. Again, so this is, say, screwed to something. Okay, so this is the first thread, this is the second thread, and so on. So this one makes contact first. So when you go and turn it on, the first thread is that one. Now this assumes that all those threads have equal stresses. Turns out empirically that's not the case. The first one shares about 38% of the load. The second one shares 25%. The third one shares 18%, and then the 6th, 7th thread are just free. So really, you don't want to have a screw with lots of threads, because essentially the stress, the critical one is the first one, which takes the most load. So when you do these calculations, if you want to find the worst case, you just find the stress in the first thread, which is the 38% load, and you can say that you've designed it for the worst case. So what we'll do is, what people do is they just put 0.38F. Okay, and then you'll put NT equals 1. NT equals 1 because remember, NT is the number of threads, but we're only analyzing the first thread, and the first thread is the one which carries 38% of the load. The last thing we want to do is know the von Mises stress, because the criteria for failure is often von Mises stress approximates it best. And so you have to take the sigma x, sigma y, sigma z, tau xy, tau yz, tau zx I wrote earlier, put it in this formula to get the von Mises stress. And then there's a part where we try to compute the factor of safety, which we'll not talk right here, but we are getting there. So once we get the von Mises stress, we can go ahead with factor of safety. Okay, so my goal is for the next time, how much time we have. I don't think we're going to take, it's 1:30. 20, I don't think it'll take 20 minutes, but I'll just solve this problem, which basically is application of all the formulas. And unlike, the first part where we had, when we did torques and normal forces and combined loading and so on, that was very conceptual, like you need to analyze. But this is not conceptual in the sense that once you have expressions for these things, it's just a matter of bookkeeping. You know the formula, you apply it, and you just keep going with that. That's why I put less stress on the theory and more stress. I want to put more stress in the questions. So here is a problem we'll solve. So a square threaded maybe power screw has a major diameter of 32 millimeters. So D is 32 millimeters, a pitch of 4 millimeters. So it's double threads. Assume a friction coefficient of 0.08. T equals 40 mm. Think, what is D? Let's get to that in just a bit. 40 mm. F equals 6.4 kilonewton per screw. Okay, so there needs to be a clarity here. Let me see what this is. So we have major diameter. No, so there's TM, DR, and D, but this is confusing because now we have, that's the major diameter. This can't be the major. It's bigger than this one, but it cannot be the major because it's 40. Is there? I think it's the, wait, I think it's, I know what it is. The collar, probably, thrust collar. TM, I think it's DC divided by, it's DC, I think. I think it's the collar diameter, which I should have stated there. Let me quickly check. Yeah, it's DC, so it should be the collar diameter. Sorry about that. That should have been more clear. This is the collar. So I should have stated that collar diameter. So this is DC. Okay, so all those things are given, and we have a bunch of things to calculate. Okay, so let's go over them one by one. This is as I said, this is all uh, applying all the theory which we have talked about so far. So thread depth, thread width, pitch diameter, minor diameter, and the lead. Okay, so I'm going to draw a figure which will help us to figure this out. So here is, this is part A. Let's choose an axis. And then we're looking at square threads. So this is what a square thread looks like. Okay, it's square. So you will have this part and this part. Would it be of the same length? This will be P divided by 2, pitch divided by 2. This will also be pitch divided by 2. There are some diameters which we need to consider. This is the major diameter. But since I drew from the distance from the axis, this is really D divided by 2, right? Because it's radius. Then we have the minor diameter, also known as the pitch diameter, dr divided by 2. And then if you draw the line midway, like this, that's going to be the pitch diameter, dp divided by 2. So what are some of the things we need? Thread depth, thread width. Okay, so I'll have a shortened notation here. TW is thread width, TD thread depth. So I think and see it's kind of obvious from the figure that thread depth in this case is P divided by 2 and P divided by 2, right? So this is P is 4, so this is going to be 2 millimeters and 2 millimeters. Okay, that's straightforward. Then we have pitch diameter, minor diameter, and lead. Pitch diameter. So the pitch diameter also happens to be the minor diameter. No, sorry, the mean diameter. Pitch diameter is the same as Tm, which is going to be I've called it dp here. So dp is going to be capital D minus p divided by 2. So there's p divided by 2 P divided by 4 here, and then P divided by 4 down there. So it's P divided by 2 when you sum them up. So this comes out to be 32 minus 4 divided by 2, which is 30 millimeters. Then we have the minor diameter, which is dr. It will be d minus p. So it's the smaller one. So d is 32, p is 4. So this is 28 millimeters. Okay, and then the last question was the lead. Okay, the lead is basically the distance the screw moves for one rotation. We are told that this is a double threaded, I think, a square threaded power screw, double threads. The key thing is double threads. So it's 2 times the pitch. This is because it's a double thread. So 2 times the pitch is 4. So lead is 8, lead is 8 mm. Okay, so that's just some kinematics of the screw or the dimensions. Okay, next, torque needed to raise and lower the load. There are a bunch of formulas which we just have to use. Torque needed to, here, copy. I'll also need the collar one. I'll show you why. So let's take this thrust collar. There is also a copy. So all these are from the formulas earlier. TR is lift. This is lower. Maybe I did a mistake. Hold on. I think it's switched. Let me check. Lifting a load, R, yeah, and lowering is PL. Lowering is PL. I think I'm right. Okay, so what we can do is we can compute. Wait, I have something. It's the opposite, right? That's what I was thinking. It's the opposite. Lifting is, no, TR is lifting, and lowering is PL, TL. Lift, yeah. Yeah, this is right. This is what I've written is right. Let me quickly check the book. TR raise the load, TL lower the load. Okay, so the better way to remember is raise and lower. Did I do a mistake here? Let me check. Lifting. Yeah, so the other way of thinking, I think this is a better way to remember it. This is raise. So raise is R, and then lowering, just called lowering. So the L. So where is the problem? Raise, lifting, raise, this is right. And then lowering is minus. Yeah, this is right. So let's go back here. Raise.
That would be like the car jack, right?
Yeah. But yeah, car jack you also have to lower later on. Lower. Okay, so that's right. So what we can do is I'm going to substitute the values. I'm just going to give you the values. dm is the mean diameter. It's 30 mm. So I think it's also the pitch diameter. So pitch, same as pitch, same as dp. So this was computed in the previous part. We have F, I think this was given per screw. So that comes out to be 6.4 kilonewtons. Then we have DC. This is the collar radius, which we were told, 40 mm. Then we need the lead, which is 8 mm, computed in part A. Then we have the friction. We're going to assume that the friction in the screw is the same as friction in the collar. So that is 0.08. Screw is same as collar. Okay, what else do we need? We have FPR. We need a. Yeah, I think everything else covered. Okay, so using these values, you get TR equals minus 0.466, sorry, TL equals minus 0.466, TR equals 15.94, and then TC equals 10.24. Okay, now this one indicates it's going to be not self-locking. Right? The condition was that TL should be greater than 0. It's not self-locking. However, the net lifting T total for lift is actually TL plus TC. So you need to apply a force equal to that to the collar end, that due to lowering without any collar. So this comes out to be TL plus TC is minus 0.466 plus 10.24 is 9.77 Newton meter, and total lower lift should be T, sorry, just lift, yeah, lift, my bad, sorry, TR plus TC, T lower should be TL plus TC. So TR plus TC is 15.94 minus plus 10.24, and then this will be minus 0.466 plus 10.24. This comes out to be 26.18 Newton meter, and this comes out to be 9.77 Newton meter. Okay, so in the absence of TC, it's not self-locking, but because it's TC, it's actually self-locking. There's enough friction for it to hold on to its place. Okay, next we need to kind of efficiency for lifting the load. That is a straightforward calculation. It's just we've been given that E equal, yeah,
Total lift or total load is greater than zero, it would be self-locking.
self-locking, yeah. FL divided by 2 pi times T. Here we'll put total lift. Total, the formula is sure.
Do both the total lift and total load have to be greater than zero?
No, the one of them is always positive.
Yeah.
But the other one is the TL is never, there's no guarantee it's positive, because this is usually true. F is a very small value, so pi dm is usually greater than FL, right?
Yeah.
But this way it's not true, because pi f dm can be greater than L, less than L. The efficiency is T0 divided by R. So here TR has to be replaced with total lift. So F is 6.4. L is 8 millimeters. Total lift or total load raised is 26.18. And so the efficiency is 0.311. So it's 31% efficient. We were able to solve A, B, C, which was basically the dimensions, the torque to lift and raise the lower the load, and then efficiency. Let's look at the body stresses, torsional and compressive. So next part is D. Torsion, stress. Okay, so for that, the expression was here, it's because of the torque. Yeah, so here what we do is we need a torque, and the torque, which we'll assume here, is there are two torques. If you remember, there was a torque due to lifting and there's a torque due to lowering. Okay, and we want to compute the maximum stress. So between the two, the lifting torque was higher than the lowering torque, so we'll just use that one. So total lift. So I'm going to change this a little bit. I will say lift. And maybe I should not put it there. Let me write it here. Since T lift was greater than T lower, we use T lift. So tau yz is 16 times T lift. T lift is 26.18 kilonewton meters, so 1000 divided by pi times, we've computed what dr was. It's the diameter of the pitch, or sorry, the root or the minimum diameter, because the minimum diameter will give the maximum stress. So 28 cube. So again, go again and see what that is. It is essentially here. So this is the minimum diameter. That's what the one use, because minimum will give a maximum stress. Okay, so this comes out to be 6.07 megapascals. Okay, there's another question asked here. It is compressive stress. So this is the stress which is compressing the screw or the fastener. So here the compressive stress is basically the one due to F acting on a cylinder of diameter dr, the minimum one. So it'll give a maximum stress. So let's do this. It's going to make some space. Yes, so next is compressive stress. Here's the formula. Let's put in the values. Okay, F is the force, and I believe we're given the force per screw, 6.4 kilonewtons. We'll use that. Times 1000 to convert newtons. Then pi dr, so dr is 28 square divided by 4. So doing the math will give me sigma y equals minus 10.39 megapascals. So that's very straightforward. Okay, so bearing stress in the first thread, let's look at the equations. So we have axial stress, we have bearing stress. This is the formula. Okay, so here's the simplified formula for bearing stress. Okay, so let's take it. So this is part E, bearing stress on the first thread. Now, I'll come to the first thread in just a bit. Let's just paste this. Okay, so this is the general formula. Okay, there's something about the first thread which you should know. So we know that from experiments, the first thread shares 38% of the load. Okay, so not all the force which is coming onto the screw is taken by the first thread. So it's distributed 38%, 25%. If you add all of them, they should come out to 100%, right? So for the first thread, and really we don't really care about second, third stress. The first one which fails is the one which we are going to design for, right? The first thread is more important. So when we want to estimate the stress, we just set the first F to be 0.38 F and NT to 1, because we're only considering the first thread, and NT is the number of threads, but we're only considering the first thread. So let's take NT equals to 1. If you solve it without this assumption, then what will happen is you'll take F to be whatever the force is, NT would be number of threads. In that case, you'll be averaging the stress across all the threads, which is not the case. The first thread takes a lot more load than the other ones. So we'll take this and go with this. So we'll have to put F equals 0.38 times F, which is 6.4. We'll take NT equals 1. Considering first thread, that's the explanation. And now it's just a matter of putting in the values. 0.38 times 6.4, pi, dr was 28, NT was 1, P is the pitch. I think the pitch was 4. So this gives me sigma x equals 41.5 megapascals. Okay, we're almost done. So this is part E. Part F, one misses stress at the critical stress element where the root of the first thread interfaces with the screw body. So to find the von Mises stress, we have this formula. If you want to write it. Okay, so part F. Okay, now let's see what we know about the stresses. Okay, sigma x, we've computed that, so that's known. What else have we computed? We have computed sigma y, tau yz. So sigma y and tau yz, sigma y, tau yz. Okay, but we need the other stresses. So let's see if we have formulas for those stresses. So if you go back over here, rather this is the summary. Okay, so tau xy and sigma z is 0. So let's put those equal to 0. Tau xy and sigma z. 0, 0. So we still have to compute tau zx, and tau zx is actually given in that formula. So if you, so tau yz is, yeah, tau zx is here. Here's tau zx. So T equals T lift, which is 26.18 megapascals, I think. Oh, sorry, Newton meter, my bad. And then since it's the first thread which is critical, we'll assume that the T is actually 38% of T lift. So 0.38 times 26.18. Tau zx, my bad. Tau zx equals 4 times 0.38 times lift divided by pi times dr is 28. Nt, since we're looking at the first thread only, it's 1. Pitch is 4. Tau zx comes out to be 4.04 megapascals. With this, we are actually ready to substitute in this equation. We have now obtained tau zx. So the last step is computing the von Mises stress. So 1 divided by square root of 2. I'm just going to substitute the values which I found, 41.5 minus of minus 10.39 square plus minus 10.39 minus 0 plus 0 minus 41.5 square plus tau 6 times tau xy square, which is 0, plus tau yz square, which is 6.07 square, and tau zx, which I just found, it's about 4.04 square. The whole thing needs to be taken a square root of, and then von Mises stress finally comes out to be 49.2 megapascal. So that's the answer. Okay, that's the stress on the first tooth, and the stresses, von Mises stress on other tooths will be smaller than this, but we'll have to design based on the maximum stress, which is going to be this one.